Hello, this video is going to be on electric fields. So what is an electric field? Well, first of all, we need to get into what is a field. Now, electric fields are going to be vector fields. And what vector fields are that you can have a vector defined at every point in space. So when you have a vector field, you can have a function, let's just call it v, of x, y, and z as inputs in 3D space, and then the output of this function for any given x, y, and z will give you a vector associated with that point in space. Now, we're already familiar with fields in gravitational fields. So a gravitational field um, just describes the force per unit mass vector for every point in space. So gravitational field is a field for a vector field where the vector is force per unit mass. And we're familiar with this in the form of little g here. So this is the gravitational field. And this is equal to the gravitational force vector divided by the mass. Now m0 here, or m naught, this is called a test mass. And then a special thing about this test mass is it has to be very small. And the reason the test mass has to be very small is because if we want to measure the gravitational field an object exerts, we want to have a small test mass because anything that's bigger than a small test mass may change the mass distribution of the thing we're trying to measure. And that will cause this gravitational field to also change. So because the test mass is very small, it will not influence or it will not change the object we're trying to measure in any way. So the gravitational field that we measure is going to be accurate. Okay, so now why do we want to know this field? Well, this field is important because, as we have seen before, we can use this field to find the force on an object given its mass at any point in space. Because we can find like for a gravitational field, we can find the gravitational force on an object given its mass just by multiplying its mass by the value of the gravitational field, gravitational field vector at that point. And so we find the gravitational force based on the field at that point and a mass. And this is very useful. So we know that charge is similar to gravity from already we can see that from Coulomb's law being similar to Newton's law of gravitation and the equation used to find gravitational force. But charges also create electric fields. So electric fields are also vector fields. So they will have a vector associated with each point in space. And instead of force per unit mass, now since electric fields are based off charges, we have force per unit charge. And this can be expressed as E, which is the electric field. So this is analogous to little g here. E is equal to the electric force here divided by a test charge. So Q0 is a test charge. And again, this test charge has to be very small in magnitude, and it has to be positive. Now, with gravity, everything attracts, so we don't need to worry about whether there's positive or negative mass because there's no such thing as negative mass. But with charges, you have positive and negative charges. And the reason this charge has to be positive is because if you had a negative charge, it would change the sign, which would mean a direction change of this force. So the electric field would be in the opposite direction, or the field wouldn't be in an opposite direction, but the force would be in an opposite direction for a negative charge. So if we want a positive charge to test the electric field for positive fields, or for electricity. So electric fields, you want a positive test charge, because that's going to be in the same, the force is going to be in the same direction as this field. Also, we want the test charge to be very small because, again, just like gravity, we don't want this test charge to influence the charge distribution of the object we're measuring. So if it's very small, it won't exert a large force on the object we're trying to measure, so it won't change the distribution of charge on that object. Now, like I said, the sign of this test charge doesn't change the direction of the electric field. It's just positive charges will have a force that's in the same direction as the electric field, and negative charges will have force in the opposite direction. Now, you'll see that it cancels out with a negative charge, but we want to use a positive charge to test for electric fields because the force is in the same direction. Now, electric fields have units of newtons per Coulomb, which you can see because newtons is force and Coulomb is charge. But this is equivalent to volts per meter, which is sometimes more common when reporting electric fields. Now these units are equivalent, they're just different representations of the same thing. Similar to how for a gravitational field, we can express it as either newtons per kilogram or the equivalent meters per second squared. So this newtons per coulomb and volts per meter are equivalent units for electric field. And again, similar to the gravitational field, we can use this electric field to find a vector and then find the vector for electric force given a charge and the electric field at a point. So this is very useful. Now we can also substitute Coulomb's law into this equation to find some proportionality relationships for electric field strength. So if we look at the magnitude of the electric field, we don't have to worry about the vector then. We find that it is just electric force divided by charge. And if we substitute Coulomb's law, we have that the electric force is equal to charge multiplied, well, we have this constant here. So we have a constant k, or 1 over 4 pi epsilon naught times the magnitudes of the charges multiplied together. So multiplied by magnitude of this test charge and divided by r squared. Now since we're dividing by this test charge here, we see that these test charges cancel out on top and bottom since they're both positive, so this absolute value doesn't actually matter there. And then we get that this electric field magnitude is going to be equal to k. So k again is this constant here. I'll save space here. I'm just writing k times q, magnitude of the charge divided by r squared. Now what does this tell us? This tells us that the magnitude of the electric field is going to be proportional to the magnitude of the charge that we're trying to find the field for. It's a direct proportion, a direct relationship. And it also tells us that the magnitude of the electric field has an inverse square relationship with the distance from the charge that it originates from. Okay, and then one more thing is that electric fields, again, follow the principle of superposition, which means that if you have multiple charges and you want to find the electric field at one point, you can find the electric field from each charge individually and add them together at the end. So that's something that we're used to, and that's just the principle of superposition, which electric fields follow. Next, let's talk about electric field lines. So field lines are a way to visually represent the electric field coming from a charge, and they follow some rules here. So field lines, first of all, they're not actual things. Like there's no field line in real life that goes from charges or between charges. It's just a representation of the electric field in a volume, in a space. And field lines really should be in 3 dimensions. We can usually only draw them in 2 dimensions. So even though we have two-dimensional field lines. Just know that field lines should extend in 3 dimensions, just like in the electric field extends in 3 dimensions. And the field lines themselves don't mean anything because the field lines are not actually there. They're just representations. So field lines follow some specific rules in that they must show the direction of the force tangent to the field line. So the direction of this electric of the electric force exerted on a charge um, is going to be tangent to a field line at all points in the field line. So this means that if we have a field line like this, let's just say it's like this, and then we have some charge here that's on the field line, then the electric force exerted on this charge is going to be tangent to the field line at the point where that charge is. Now, this charge doesn't have to be on a field line. Like, let's just say we draw, let's just say we draw field lines like this, and then we happen to have a charge that's right here in between them. Now remember, like I said, field lines are only a representation of the electric field, which means that the field line themselves, the lines themselves don't represent, like, they aren't actually there. So just because it's in between two field lines doesn't mean that there's no electric field there. It just means that we haven't chosen to draw a field line at that location, but it'll still be tangent to where there, if there was a field line there, this force would be tangent to that field line. Now, another rule for drawing electric fields is that it starts on a positive charge and ends on negative charges here. So they must start on positive and end on negative. Now, a consequence of these two rules is that one, field lines, they never cross. So you can never have field lines that cross like this. Because why not? Well, if you think about this point right here, since field lines represent the direction of electric force, if you have a charge at this point, you can't have a force that's going in 2 directions at once, which means that they can never cross. Also, this means that field lines can never form loops. So if you have some positive charge here, you can never have a field line that looks like that, because then, like, you can't have it start here and end here because they both have to be going outwards and they can never cross. So field lines don't form loops and they can't cross. So I'll write that here. So field lines cannot cross or loop. Okay. Another thing about field lines is that the magnitude of this electric field represented by the field lines is going to be proportional. It's proportional to the number of field lines per unit of cross-sectional area perpendicular to those lines. So it's proportional to the number of field lines intersecting a so it's proportional to the number of field lines intersecting a cross-sectional area. So per cross-sectional area of space perpendicular to those field lines. And again, this goes back to field lines being in 3 dimensions. So if you had some charge here, and then you have field lines coming off of it, notice that if you have a plane that's perpendicular to this charge here, I'll draw this in another color. Perpendicular to this charge here, the field line, the strength of this field at this point is going to be, if we look at it, it'll be basically the density of field lines that are that cross through this cross-sectional area and are perpendicular to it. So because this is in 3D space, you can't see the strength of these electric fields directly from a 2D representation, but the density of field lines still indicates the strength of the field. It's just not directly proportional in 2D. So that means the density is related to, but not proportional to, the strength of field in 2D. So as you see, closer to this charge, the field lines are closer together, which means that they are going to be stronger. And further away from this charge, the field lines are further apart, which means that they are going to be equal. I mean, they're going to be weaker, further apart from this charge because they're further. The field lines themselves are further apart. And then again, like I said, the field lines themselves are not actually there. So you don't the like how close a charge is to a specific field line does not matter to its to the strength of the field at that point. So like these two charges, even though they're the same, like even though one is on a field line and one is off of it, they both have the same magnitude of force in electric field because the density of field lines at that point is the same. So only the density of field lines matter for strength, not if a charge is on a field line itself. Okay. And then one more thing, notice that all these lines I've drawn so far are perpendicular to this charge. Now one way that you can think about this being true is if you put a charge here, a test charge, really close to it, it's so close that this force is going to be straight away from this charge. Now I drew that kind of crooked, but it's going to be directly away from this charge, which means that it should be perpendicular right next to the charge. And then you also, later you'll see that because it's perpendicular, so this charge has an equal potential plane, like this equal potential line is perpendicular to these field lines too, but you'll learn about that later when you get to electric potential. But now just know that these field lines are perpendicular to charges. So these field lines cannot extend like that because then it would not be perpendicular to the surface of the charge. And it also doesn't make sense for an object to shoot off in some random direction that's not directly away from the charge when it's right next to it. Okay, so now let me give some examples of drawing electric fields. So like we saw before, when you have a positive charge here, you have electric fields that go straight off of this charge and perpendicular. So this is what field lines for a positive charge could look like. Now, like I said before, the density indicates the strength of this field, and so if you have a charge here that's like Q, and then you have a charge here that's like 2Q, you'll know that the density of field lines is going to be greater. So you have more field lines extending from this charge than one with a smaller charge. And so from this greater density, you can see that this charge is greater than this other charge here. Now for negative charges, you can still draw field lines and it'll look almost the same except that they'll be going into the charge. Because like we said in the rules for drawing field lines, they start at positive and end at negative. And again, the density here indicates the strength of this charge. Now you can also draw field lines showing the electric charge between two different charges here. So right now we've shown isolated charges, but what if you have like a positive charge right next to a negative charge? And for now we'll assume that these have equal strength. Well, the field line will go from positive to negative, and it starts off perpendicular at both ends, but it will curve like this because again, this field line represents, so tangent to this field line is going to be the force at a given charge. So let's just say you have a charge right here that's positive again. You'll experience a force from this positive charge in this direction, and the negative charge will attract it in this direction here. So the net force is going to be horizontal, which is why this point of that field line is horizontal. But let's just say you have a charge right here. This positive charge is going to repel it, but this negative charge, which is weaker because it's further away, is going to attract it. So this net force here is actually going to be slightly off of directly away from this positive charge, which is why this field line here, it curves. And then, so these field lines will curve like that, and they'll always start and end perpendicular, but they'll curve away. So they'll curve and form like this pattern here. And then here, field lines don't actually abruptly end in space. It's just we can't draw this far, and so in saving like space for the drawing, we'll just draw the field lines as if they're continuing on, but we don't actually draw that they're continuing on. So this is what field lines would look like for two like equally charged positive and negative objects. And again, these charges don't have to start on field lines. Like you would have a charge right here, and then the direction of the electric force will be tangent to if there was a field line right here. It'll be tangent to that imaginary field line because the electric field exists at all points in space. And again, these curve because there's two different charges acting on any test charge placed in it. So these lines aren't going to be perfectly straight. They'll depend on the distance to each charge. Now this is what two different charges look like. But if you have two like charges, let's just say you have two positive charges here, what will the field lines look like then? Well, first they have to extend outwards from all these charges here. So we know that it's going to be perpendicular and it'll extend outward. And then I won't count these, but let's just assume that these have the same potential or the same charge on them. Now we know that this, they can't go into each other because we say they can't form loops and they have to end in a negative. So this, it repels each other. These charges repel, so it's viewed in the, so these don't cross. But these field lines, because these charges repel, you see that the field lines also show the repulsion of these like charges here. So the field lines will look something like this. Where they're still going outwards from this positive charge, but they repel at the middle here. And then notice here that this place has very low density in the middle here, right here, because the net charge on this object, it'll have a charge like, it'll have two forces here that cancel out straight in the middle. So there's no net electric field here, which is why the density here is very low, and it's basically zero if we view it like this. Right in the middle of these two equally charged charges here. So density here is zero in the middle, but as you go out, you see that these field lines show the repulsion. And then these could be two negative charges as well, and it would show the same, except the arrows would be pointing towards the charges instead of away. Now, what if these charges weren't the same potential? So what if you had a stronger charge and a weaker charge? So let's just say you have a strong positive charge here. Positive charge, we'll call that 2Q. And then a weaker negative charge, we'll call that just Q. While this positive charge, we know from the density of field lines, will have a greater density of field lines coming off of it because it's stronger in magnitude, and this will have a fewer number of field lines going into it. Now, what does this look like then? Well, they'll still go from positive to negative, but since there's a greater number of field lines starting from the positive one, it'll curve so that it's not symmetric. So let me redraw these actually because to show it better. So this here curves so that it meets the, and so these field lines will look something like this, to where it's asymmetric instead of being symmetric like the example above where they curve straight down the middle. So now this curve here is going to cause the field lines to be curved closer to the negative charge, And so this negative charge, we see that the more field lines originate from this positive charge than go into the negative charge. So these have to be curved curved so that these field lines can start at the positive and end at the negative, but still have more starting from the positive than going into the negative here. So that's what that will look like. And then if we have two like charges, so this time let's just say they're negative for the sake of it, or sorry, that's positive. Let's just say they're negative, and then this is Q here, and then we have a charge here that's like 2Q. We know that we have more field lines originating or going into this charge, and fewer field lines going out of this charge, going into the other charge. So this will have fewer field lines. But then they're still going to repel. So what this will look like is this will curve less than the other one we've seen. So this curves less, and then this charge here, it curves more on the charge with a smaller magnitude. So these curve at a greater degree. And so now these will go into the charge again because it's negative, but they curve more, as you can see in both cases, with a smaller charge. And so whereas before on top here we see that this intersection between them form basically a straight line, but here we see that it forms this curve because the charges are not equal. Now, so far we've only looked at point charges, but what about like plates? Let's just say we have a plate of charges here. Well, let's say it's positive charges that extends infinitely far. So this keeps on going. And then these are evenly distributed. Now, what will the field lines look like for this? Since it extends infinitely far, if we put like a charge right here, first of all, it's going to be perpendicular. And second of all, we have these forces from these particles that here, since it's symmetric, these will all cancel out because the force from like one particle over here will get canceled out from the force of a particle on the other side since it extends infinitely far. So that means the net force here is always going to be perpendicular to this plate. So we have field lines here that are evenly spaced and going perpendicular and straight away from this plate, assuming that this plate extends infinitely far. However, what if we have a plate that does not extend infinitely far? So let's just say we have this small little plate right here. Again, I'll just put it positive, but this could be negative as well. We start off perpendicular because we know that it must be perpendicular. Sorry, this should be perpendicular here. But as you get further away, this curves outwards from the middle. Maybe not that much. Start to curve outward from the middle, and the further away it is from the middle, the more dramatically it curves. And now, why does it curve outward from the middle? Well, first of all, you know that this field must be getting weaker as you get further away. So it should curve away from each other. The lines should curve away from each other to lower the density of the lines. Also, if you have a point that's off center, like let's just say we have a point here, we'll have repulsive forces from this particle, but then there'll be more particles to the left of this test charge than to the right of it, which means the net force on this test charge is going to be not straight or not perpendicular, but at an angle away from the center of this plate. So that's why these curve as you get further away. Now we can also draw a charge between two plates. So again, let's go back to these two plates that extend infinitely. And so let's just say this is a positive plate and this is a negative plate. So negative and then positive, the field lines would go from negative to positive, and so they would just go straight down here like this. And then it would extend outwards from the other side, and then inwards on this side. And now when you're drawing these, make sure that these are touching the object. Now I'm drawing this on a screen, so it's a bit hard to be super precise, but field lines, they must originate from a positive object or end in a negative object. They can't just like start off in randomly in space. Okay, so those are field lines, and then again, these are assuming that these plates extend very far away, so that we don't have like this uneven distribution of charges on either side of an object. Now let's just say, what happens when you release a test charge or a charged object in an electric field? Now let's just say you start off with an object here. The force is going to be straight down, and it always is straight down, so the path that this object takes will be straight downwards. However, let's just say you're shooting like a proton through this. So you have this charge here, and it starts off with this initial velocity like that. So this is v naught. What path will this take? Well, when the charge goes through this field, there will be a net force downwards on it because of the electric field, but it has an initial velocity. So the charge will follow a curved path downwards as a result of this field. But notice that this charge doesn't have to follow the field exactly, because the field only describes the force on it, or the electric field only produces a force on it, which in turn produces is associated with an acceleration on an object with mass. And so these field lines show the acceleration of an object, not the velocity of an object. So the velocity, an object can move through field lines, but the acceleration is always going to be in the same direction as field lines, and so it's going to curve in the direction of field lines, but that doesn't mean it has to follow field lines. So like if you have an object starting right here, the field lines are all straight, so it will just move straight outwards. But if you have like an object like starting right here, it'll accelerate in this direction, but then it doesn't immediately curve to follow this field line, because while it accelerates in this direction, like at this location, the force on it is going to be in this direction, not directly downwards, which would be needed for it to curve. So it will accelerate, and then it could like overshoot and then hit this charge like that. But that doesn't mean it has to follow these field lines exactly. Okay, so those are the basics for electric fields.